Okay, so what we'll do today is I'm going to recap what I learned on Tuesday. Remember on Tuesday I was writing the program for the homework assignment and it wasn't working, and then for some reason the debugger didn't seem to be cooperating as well. So some of you follow me to the lab and then we actually figure out everything. And so it turned out that there are two important things that I learned from that. One is make sure optimization is turned off when you're debugging your program, okay? Because one of the problems that I encountered was I was able to set up breakpoints, but because the compiler has optimized the program to store certain values in registers instead of in the actual local variables, so when I try to look up the actual values of the local variables, they have not changed, okay? But that's because the compiler has optimized the access to the local variables so that some of the values are actually stored only in registers, but not in the memory corresponding to the local variables. So that made debugging a lot harder because there's no way to tell actually what the values are corresponding to the local variables. So the first thing you want to do when you're debugging a program is to turn off optimization. And that's also partially why in code blocks you have two profiles. One is production and one is for debugging. Okay, the debug profile would actually turn off optimization for you. Okay, so that's the first thing I learned. And then the second one is the boundary checking ability. It didn't work the way I expected it. So when you compare the product to the number before the multiplication, that one doesn't catch all the cases, at least not with my program. Okay. And I have heard with some people it does work correctly, but it didn't work correctly in my case. But once I compared to exactly the number that I really should be comparing against, that part was okay. It wasn't too difficult. Okay. Are there any questions about that? Does anyone want to see what that program looked like, when it's all done? No? Okay, cool. So I can show you that program. Why would I want to know? Okay, and I think it's in the folder under downloads, ATOF. So there we go. This is the entire program. You guys have seen most of it already, so most of this should look familiar. Let me turn on line numbers. There we go. Okay, so the structure is about the same. Not sure whether last time we had an E2 already. I think we did. There's is digit, parse sign, parse mantissa, and then parse exponent. So all of those, I think we did correctly already. We checked everything. And then it's the conversion, while E10 is positive. That's the conversion when the exponent of 10 ends up to be positive, not 0, but it has to be positive, like 1, 2, 3, 4, and so on. And this is the logic. And one part that was not working before was detecting that I am running out of bits to represent the number after I keep multiplying 10 to the number, which is not something that you guys have to worry about. Why not? Because in your homework assignment, yeah, go ahead. Because you guys have a very small exponent where that limit would never happen, okay? So the bug that I was dealing with would only affect programs that try to handle the most general cases of a floating point number. But I tried to do that. So what I ended up doing, this code does work, okay? So when you look up max 10 is basically a constant, but the constant is defined up here. I just use a good old-fashioned macro definition instead of the const int kind of definition. So I use uin64_t to typecast the zeros. So I know I'm dealing with 64 bits. I subtract one from 0 to get the highest possible value when I'm only having 64 bits. Is that part okay? Does everybody understand why a subtraction would end up having the largest value? Is that okay? All right. And then I just take the value, divide it by 10, because if I multiply this number by 10, then I'll be out. Okay? So that's how I determine what is the last number that I can deal with before I multiply by 10 again. And then the loop basically is going the same way. This part is basically saying as long as, I know the program worked. So this is when, oh, when it's positive. So I have to multiply by 10. Oh, okay, I know exactly what it is. Okay, so this loop is for making room for another multiplication by 10. In other words, if M10 is at least max 10, it means if I multiply that number by 10 again, I'll be running out of bits. So in order to make room for another multiplication by 10, I have to shift the bits out of it so that I can make the room to have another multiplication by 10. So that's why in this loop we have a right shift by 2, and also for each right shift by 2, I have to remember to add 1 to E2 because I'm not trying to change the value that we are representing. I'm only changing how it is represented. Is that part okay? All right. And the rest is actually pretty easy because the rest is really just keep multiplying by 10 and then just say that we have another exponent of 10 taken care of until we don't have any exponent of 10 left. In other words, when E10 becomes 0, we are all done. Yep.
I forgot to ask on Tuesday. What's the difference between doing a define and just making a constant variable?
This is a feature, or this is what we needed to do before the C standard included like const ints and stuff like that. It's done at a different time. When you say const int, it is done by the compiler. This is a macro. It is done by the C preprocessor. So effectively, it will still do the same thing. It's just that in this case, I don't know. It should be doable, at using a const here, a global const.
Because I was using constant over compiler. I was just wondering if there's a benefit to doing one or the other.
If you use a const,
isn't it uint? Isn't it uint right now?
Isn't it?
Uint 64.
Yeah.
So could you do a const uint 64?
Yeah, you can probably do the same thing. The program would work exactly the same if you were to change this line to use a uint64 constant. So if you change this to uint64 underscore t, and I would strongly suggest you making a const ahead of it so that you don't try to change the constant. That would probably work exactly the same. The difference is this part here is actually done by the preprocessor. In other words, every single time it sees max 10, like here, it is expanded to the definition of the macro before the compiler gets a hold of it. As opposed to a const int definition, like this one, where, this is missing an equal symbol. So this is a compiled concept, which means max 10 is actually quote unquote a variable, even though it's a const, but it is conceptually speaking, it is still a variable. So every variable has an address, and you can still cast it to a non-const uint64 underscore t and change it. As opposed to the other one, which is really just expanding the text definition of max 10. So even though in this program it wouldn't make any difference, but fundamentally the mechanism itself is entirely different.
That sounds cool.
Yeah. So in this program, either way would work. So are there any questions about E10 is positive? That's the conversion, okay? When E10 is negative, it's about the same, except I have to take into consideration whether to round up or round down the number, okay? Other than that, the program itself, that's also normalized, which is a little bit longer. So normalized is the logic to make sure that we end up with a 53-bit mantissa, and then we do all the shifting, and then we adjust the exponent of 2, and then we make everything fit into a double precision floating point number. Yes?
In one of your write-ups, you talked about rounding the binary division. You don't expect us to do that. Dividing by 2 and rounding.
Correct. So in this case, I did not do the rounding in the base 2 division, which is this one here. So let's see, if you were to do that, you will have to remember whether your shifting a 1 or a 0 out, and then you add 1 or not add 1 to the part that is remaining. Did you do that? Or
You can do it just with mod, right?
you can just do it with a mod. Or even better, you can do it with a bitwise AND with 1. Then you can just see whether you shifted out of 1 or 0. Okay, so if I were to do the actual rounding, then it would be it will be like this. It only has to be an unsigned. Well, might as well make it a UN64 too, because of the bitwise AND. Okay. And you would just make it a PTR points to M10, and then a bitwise AND with 1. So after you do the shifting, then you say PTR points to M10 plus equal to C. So that will take care of the rounding. Okay. So, but that's basically the entire program. Are there any questions about this part? Yep.
Are you recording?
I believe so. Let me double check. Yep, I am in fact recording. Any questions about this part? So this part is run after we have a exponent of 10 of 0. So the main program, or the main part of ATOF, is just this. The first part is initializing the pointer, the character pointer. Then we parse the sign, we parse the mantissa, and then we parse the exponent. So by the time we get to here, by the time we get to line 150, we should have all the major components already done. Then we say, okay, the number has an exponent. The exponent of a 2 is by default a 0. If E10 is greater than 0, then we call this subroutine to take care of decrementing E10 by multiplying 10 for each iteration. If E10 is less than 0, then we call this subroutine here until E10 is 0. So we keep dividing by 10 until and change the exponent until E10 is 0. So by the time we get to the normalized subroutine, E10 should be exactly 0. So that's the time when we have to do all the shifting to make sure that we have a mantissa that only has exactly 53 bits. And then we deal with bit 52, the most significant bit, turn it into a 0. And then we calculate what exponent that we have to use in the double precision floating point number, and then what the sign is, shift everything into the right place, do a bitwise OR, and then we are all done. Okay, which is done by the last part of normalize. So the last part of normalize is doing exactly that. This is a statement to take care of, to make sure that we don't have a bit 52 anymore, or bit 52 is guaranteed to be a 0. There are many ways to do it, because we are guaranteed that M10 has that bit being a 1. You can do an exclusive OR with 1 shifted 52 times. That works. But in general, if you want to clear a bit so that no matter what it was before it becomes a 0, this is the best way to do it. Okay, so exclusive OR works, no problem. Subtraction even works in this case, because you're guaranteed that number has bit 52 being a 1, so a subtraction will work as well. But this is the most general way to clear a single bit, because this will work regardless of whether it had a 0 to begin with or whether it has a 1 to begin with. So the way this works is I use a 1 shifted 52 times, and then this is a bitwise NOT operation. In other words, the highlighted part that on the projector is going to be a number with all 1s except for bit 52. Is that okay? Because this part, without the bitwise NOT on the outside, this part here is going to be a 64-bit number with all 0s except for bit 52, which is a 1. Is that okay? But since we perform a bitwise NOT or bitwise negation on the outside, it turns all the 1s into 0s and all the 0s into 1. So in this case, we will have all 1s except for bit 52. What do we do with this constant? we do a bitwise AND with a 53-bit number, or whatever this side turns out to be. So what we will end up doing is for every bit with a 1, something and 1 is whatever that something was, so we preserve the original bit. When we do an AND 0, then we clear that bit. So only one bit is cleared in this case. Is that okay or not? All right. And then this part here is just for calculating what bit pattern do we need to represent the exponent. So it has to do with the fact that the actual exponent of 2 is this quantity, but the way E is represented is it is offset by 1023. So that's why we have to add 1023, which is the offset, but we also have to add 52 because the implicit point of the mantissa was originally all the way to the right-hand side. But we wanted to go all the way between bit 51 and bit 52, so we have an implicit right shift 52 times. So this plus 52 is to take care of the implicit shift to the right-hand side 52 times. Is that okay? And then the last statement is over here. In this specific case, you can replace all the bitwise OR, which is a single vertical bar, with an addition. It will still work because each component is guaranteed to only have one or designated bits being non-zeros. So a bitwise a bitwise OR versus a plus will work exactly the same way. Any questions about this part, about the normalized subroutine? Questions? Okay. So for those of you who did watch me do this entire thing on Tuesday, you probably remember that I did not write the entire thing first and then just run it and have my fingers crossed and hope that it works. Right? So what did I do instead? Some of you showed up on Tuesday. Yep, I only do it in small pieces. Until I get all the values right from parsing, I don't even bother to write the conversion. And the debugger turned out to be really useful because once I figure out, oh, it's not a compiler issue, but it has to do with optimization, I turn off optimization, and then the debugger worked flawlessly. Yep.
Will you be posting the solution?
I can post this. So this is ATOF. I can just go ahead and post this. Before I post it, it doesn't hurt to double check, right? And I also changed main a little bit. I explained that in my video on Tuesday as well, so you can watch that one, or I can just kind of go over this really quickly. So I got really tired of changing the program, recompile so that I can have a new test case. So what I did was to add ARGC and ARGV to main. These two guys, ARGC and ARGV. And these are actually not new to main. Every single main already had these passed. But when you declare main as a function with no parameters, you just chose to ignore that. But it has always, these two parameters, these two along with some other parameters, are always passed to main. It's just that with most programs, okay, you can choose not to use it. You can just say, oh, main, open and close paren, and just say that I'm choosing not to use these. But in this program, I chose to use them. ARGC is reporting how many options, how many things is on the command line when I ran this program. Okay, so it's a counter basically. It is at least one because the command itself is taking up the first entry. And then anything in addition to that will take up additional entries. ARGV is telling you, ARGV is an array of strings basically. And ARGV bracket 0, the first string, is the command itself. ARGV bracket 1 is the actual first argument. ARGV2 is the second argument, and so on. So by doing this, I can now make the program a lot more flexible because instead of hard coding what I'm using as test cases as these two, I can now refer to ARGV1 to be the first one, ARGV2 as the second one. So without recompiling the program, I can now test various test cases. So that's kind of handy, okay? You know, it's not required, but it's kind of handy. Okay, so with this, I'm gonna test the program. So now I can supply, you know, actual numbers like 1 and 3, okay? So 1 times 3 is 3, okay, no big deal, you got it. 2 times 3, okay, it just ignore the backslash. 2 times 3 is 6, okay, that worked. So now we can try something a little bit more tricky. What about 0, 0, 2, okay? That's also 2, no big deal, we figure it out. 2.3 times 3.6, I think that's right, okay? So now you can try, you know, something even more tricky. In your homework, I think I said that I would not exceed 5 as the exponent of 10, right? And then with the mantissa, it cannot be more than 9 either, right? Okay, so we can test this one, and then it can only go as far as -5, as far as the exponent of 10 is concerned. So in this case, I think we got the right number. You know, the magnitude looks right to me. Because the E5 cancels out the E -5, so we are really only looking at 1.3 times 3.6, and that looks about right. Okay, but this program also exercises the logic that I just talked about. So if you give it a really large exponent of 10, anything more than 21 is going to trigger that logic. And then on the other side, we have something that is exactly the opposite. It also works. You can type it in and see if it works. But this also tells you that, hey, something is not right. How come this number is not exactly the value that we want it to be? Well, how come it's not the 1, 3, and then followed by all zeros? We have some rounding issues. Yep. But that is to be expected. Yep.
And B is 0.0000.
Because in this notation, it's not using the scientific notation, because that number has, what, 48 zeros before something that is non-zero. So that's why it shows up as quote-unquote 0. But when you look at the product, it is still correct. So that means, you know, the magnitude, at least, of the numbers are correct. Yep. Yep. So yeah, go ahead.
How does our function stands comparing to the standard library provided ATOF? Is it like better, worse, faster, or it's just?
Well, we can.
There is a standard ATOF.
That's a good question. You want to compare against the actual ATOF, right? So we can CP main to standard.c, and then change this one so that we don't have to call our own ATOF, which means, you know, this is going to be the actual F portion, and then we also want to get rid of UFI, because now we are going to include whatever has ATOF, which of course I cannot remember. So you just man ATOF. It tells you it's in standard lib. Okay. stdlib.h. There we go. And I think it doesn't need to link with anything special, so we'll give it a try first. So -o standard.c. Oh, of course, okay, because I'm not including that thing. So we'll just have that. There we go. Oh, any of the .f, you know, we want to remove. So how do we do that in VI? Remove all the .f's. Okay, from here to the end, substitute .f with nothing. That is why I use VI. And this is only one of the many nifty little things you can do with VI. Okay, there we go, standard. Oh, we have to give it the 2 numbers, because if you don't give it the numbers, it just doesn't process anything. It silently just exits the program. So we have to give it exactly the same numbers. Hey, that's not bad. It gave us exactly the same thing. So the official ATOF did exactly the same thing. In fact, it's exact. Well, I'm just glad that it's not like super problematic. So are there any questions about this one? Did you guys have any major problems with the program when you're writing it? What are those problems related to? So bit shifting, okay. Okay, so many of you may not have exposure to bitwise operations from your C++ class. Would that be a good description of the majority of the problem has to do with bit manipulation? Yep.
I just had trouble understanding
The conversion, the concept itself. Is it better now?
Yeah.
Okay. Well, that's good because that means the homework assignment did its job. Because the whole point is we're not going to rewrite. There's no point in rewriting ATOF, which is probably the source code is somewhere available, right? You can just dig it up. The whole point is to understand what is a floating point number and how it is representing a value, so that we can go through this whole process and just figure out, okay, this is the base 10 representation, but in the process of changing the representation into base 2 floating point number representation, you have to understand it. Even with all the boundaries in place, like the exponent can only go from -5 to 5, you still have to understand, okay, we are trying to get rid of the exponent of 10. How do we get rid of it? Okay, we keep multiplying the mantissa by 10, and then we subtract 1 from the base 10 exponent. You still have to understand the shifting part, because in the end, you still have to shift everything so that it takes up exactly 53 bits. And then you get rid of the 1 point, have the remaining, so in the process, you're understanding what is a double precision floating point number. Okay. Any other, yep?
So why didn't the original boundary work, greater than, if it's less than or equal to?
Why that
M
didn't work?
times 10 is less than or equal to?
Why that didn't work?
Yeah.
Because I think sometimes you can get a result where that condition is false, but you're still actually out of the range. You're not ready to multiply by 10 again. The loop exits too early. That would be my suspicion. Yep.
So how are double precision floating point numbers added, like with their binary values? How would that, is that like?
How they are added?
Yeah, is that really complicated?
That's a worse homework assignment. The conversion is an easy homework assignment when it comes to actually the calculation. It's a lot harder. Because when you look at the double precision floating point number, the implicit point can be anywhere, right? But before you can do any addition or subtraction, they have to line up first. So you have to express the smaller number so that it lines up the smaller being only in magnitude, okay, not in sign, okay. So in terms of absolute value, just the number itself, the magnitude, you have to line up the smaller number so that the binary point is exactly at the same place as the larger number. Then you can do the addition or the subtraction. So you have to shift a whole bunch of times before you can actually do the addition or the subtraction. And then the result of that may need some shifting around too, because remember, your mantissa has to have exactly 53 bits. So if after the subtraction, if those two numbers are really close, then you will end up with a much smaller number. Then you're guaranteed that you have to shift the numbers around a little bit again before it goes back into the double precision floating point number format. So it really is a lot of operation, and that's why in the earlier days, any program that makes use of floating point numbers are very slow to execute. Because every single time you do a multiplication, addition, or subtraction, or division with a double precision floating point number, it takes up a lot of time. Is that okay? How many people are old enough to remember those stand-alone MP3 players? I think I got one of the first batch of those things. It was like, oh, this is so cool. It doesn't have a cassette tape in it. right? I mean, CD players are kind of like an in-between thing, but I never really got into CD players that much because they're bulky compared to cassette tape players. Even though it's all digital and good, but the moment you start to run or do any motion, a cassette tape player doesn't really bother. It's not bothered by motion if you're running, jogging, or whatnot. But a CD player doesn't like that at all. And they come up with all kinds of mechanisms like buffering it and do all kinds of anti-vibration mechanism. None of that works all the time, okay? But when they first came up with MP3 players, I go like, wow, this is the technology. Solid state, it will stand up to anything. So anyway, when MP3 came up, MP3 is not open source, by the way. Okay, MP3 or the way to do encoding using MP3 is actually patented. MP3, okay, you can look it up. MP3 encoding patent, MP3 patent, that should be enough to find it. Okay, so you can see, oh, this is, I'm interested in when it's going to expire, but it is patented, which basically is saying, what it is really saying is, if you are a developer and then you look up the encoding mechanism and then you write your own decoder, you can be sued. Okay? What?
The first link just says that it's decoding and encoding technology is patent-free in the European Union. So just in the United States, it's patent.
Just in the United States, right? There are a lot of things like that. This is not the only one. Like the DMCA does not exist in Europe. The DMCA, the Digital Millennium Copyright Act, does not exist in Europe. So in the United States, any quote-unquote attempt to circumvent copy protection mechanisms is illegal. Whether you actually use it to pirate something does not even matter. If you do research on that particular subject matter, you can be sued. Okay, whether you can be thrown into prison or not, that's a whole different story. Whether it's a civil or criminal, type of a violation, I don't know for sure. Okay, but just the act of trying to do it is enough, which led to a really interesting problem. In terms of laws, you are allowed to make a copy of things that you bought. So let's say you went to the store, you bought a DVD, like the physical, actual DVD, and you say, well, just in case I scratch it or destroy it in some way, I want to back it up. By law, you are allowed to do it. But the DVD is encrypted. So you will first have to illegally decipher it first, and then you can legally make a copy of it. So that's a lot of strange things. But anyway, the point is, MP3 encoding and decoding does not involve floating point number calculations, surprisingly. Okay, it's all integer math, fixed point and integer math. So it can be done very efficiently. A open source standard to MP3 in the name of, what is the name of that thing? Huh? Yeah, org vorbis. Vorbis. Yeah, OGG is only describing the container, and then vorbis is the actual encoding mechanism. So vorbis, okay, not PGG, it's OGG. There we go. So org vorbis is actually the open source standard for audio encoding and decoding. It is used a lot in games because it is license free, it's patent free. People can use it any way they want without getting sued. And also the quality is at least comparable to MP3 using the same bits per second. Okay, so if you say, okay, I just want to have 128 kilobits per second, org vorbis is reported to give you better encoding. The quality of the music is better when you are deciphering it. Okay, when you decode it. But the problem is org vorbis involves floating point number calculations. And as a result, those little tiny MP3 players, which only has a limited processing power, could not implement org vorbis. Okay, but now you have octa-core cell phones, so they can deal with any format. But back in the good old days when you have like a, standalone MP3 players, they could not do all the 4 bits because of floating point numbers. So the whole point is, when resources is limited, processing resources wise, you usually have to, avoid the use of floating point numbers. And figure out, how to massage the math in order to only use integer arithmetics. Okay, so there we go. So this is all done, and let me upload it right away so I can do this before I forget. Okay, zip it up first. And we'll just upload it to the shared folder. Not this one. I will put it into examples, okay? So we'll just put it over here, upload. It's called downloads ATOF. Done. That's it. There we go. So now it's on the on my drive, and you guys can download it, look at it, comment on it, do whatever you want. Okay, so with this done, I am going to talk about the practice exam because I want to have the exam next Thursday. Okay, so you have 1 week to get ready for the exam. And I'm going to use the fall 16 exam 1 as your practice exam. So here we go. I think I just got it open on the other side too, but it's okay. All right, first of all, it is open book and open notes. Have I talked about this part already? No? Okay. So this is going to be open book and open notes. You can bring anything that is printed or handwritten prior to the test. Okay? And you guys can work together too. You can just kind of work together to come up with whatever material you want to bring. But if you're working in a group of 5, you want to make a copy of 5 of those things. Because I don't want people to share notes during the test. So no sharing during the test. If you have something that you want as a group to use, make photocopies, okay? Anything that is printed or handwritten prior to the test. If you like a certain screen, in the screen recording, take a screenshot of that, print it out, okay? That's fine. If you want to make a collage, okay, of all the different things and put it onto one single page, that's okay too. If you find 20 textbooks that you think, oh, these things are really helpful, bring those with you. Okay? I don't, well, okay, if it doesn't fit in the classroom, then I might have a problem with that, okay? But the point is, you can bring anything you want, as long as it is printed, no electronics. You can bring a basic calculator if you want to. I don't think it's going to be really helpful, but if you decide that a basic calculator is going to be useful, you can bring that. No cell phones, no laptops, no tablets, that sort of thing. The assessment is individual. This is going back to academic integrity. Okay. Use additional sheets of paper if necessary. So that means bring your own additional sheets of paper. I will give you the space to write the answer, but sometimes you may say, "Oh, okay, this is wrong. I want to open up. I want to use a new sheet of paper to write my answer." So bring your paper. Write legibly. I cannot give points to answers that I cannot interpret without post-exam explanation. Questions do not have equal weight. If they do have equal weight, I will write it too. They do have equal weight. In this particular case, there are 4 questions, and the exam accounts for 20% of your final grade. So before the exam, I'm just going to repeat something in the syllabus. Okay, I'm assuming that you guys all read the syllabus, because there will be that question popping up again, like usually right after the exam. So how many points do you need, or what is the percentage between an A and a B? So here's the A, here's the B, so where is this boundary?
87.5.
Yep, 87.5%, which is not off too much from your other classes, which is what, usually 90%? And you have to ask those professors, why 90%? I don't know. I don't use 90%. Okay, so the boundary between the B and the C is, you just subtract 25% from this, you get 62.5. And then the C and the D, the boundary between these two is 37.5%. And then between the D and the F is 12.5%. But the reason why I can do this is because when I grade your answers, for each answer, I'm only going to, I'm also using the same scale. I'm using the scale of, yes, this is a perfect answer, cannot be any better, okay? This is the correct answer. B means, well, there's some omission or some minor mistakes. C means, well, it is still showing sufficient understanding of what I'm really testing, but it is showing a significant amount of errors or omissions, okay? Missing stuff. D means, it is not showing sufficient understanding of the topic that I'm really asking for. And F usually means there's no answer, or the answer does not show any understanding whatsoever. Okay? But because I use the same scale, okay, usually this is 0 points, 1, 2, 3, 4, for each question, for each part of a question. So I can just use exactly the same scale as far as your final grade is concerned. Is that okay? In other words, for everything that I grade, I'm using the GPA system. So by using the average of the GPAs of each individual thing that I grade, your final grade is just a big average of the individual work. Is that making any sense? So, okay. All right. Because I know that some people will ask about this right after the test. Because it's like, oh, I think I just got 1/2 of those questions. Well, then we put that person smack in the middle, but in the C. As opposed to a 50% in a normal class, which will be, is that an F?
Yeah.
Okay. But I have to tell you that the percentage of A, B, C, D, F tends to be about the same as all of the other classes at UC Davis. Okay, so the kind of question that I might ask you is everything up to and including the process of discussion, but excluding floating point numbers. Okay, unless the entire class unanimously okay. Okay, it's late. My translation center is not working very efficiently right now. So unless the entire class agrees, I'm not going to include the floating point numbers. Okay, so we have at least a few people saying no, so I'm not going to include it. Okay, so we'll just have everything included, everything up to the processor, the last processor discussion included. All right, so this is the first question, which is based on a edge-sensitive D flip-flop. This is copied exactly from the notes. So the question is it possible for Q and /Q, this is Q, this is /Q, both to be 1s? If so, specify the sequence of input states that makes this happen. A sequence would be in the rows, the rows of input pins stating which row rows of input pin states where each row represents a step in the sequence. Okay, so you have to tell me, first make the clock 0, but also make sure that D is also 0. Next, make the clock 0, remain 0, but change D to 1, and so on. So you're basically giving me the state changes necessary to have the desirable output. Okay, so what is going to be your answer? Is it possible for Q and not Q both to be 1s? In this case, if it is not possible, you have to explain why that is not possible.
How do you know without logic?
Well, because you got this gray matter thing, right? Well, logic won't really help you in this case either, because if it's a sequence of operations, logic, unless you enumerate all the possible sequences, logic won't be able to help. Yes?
I'm going to say it's not possible.
Okay.
Because G5 and G6 both negate both of their outputs.
That is correct. Okay, so Q and not Q being both ones means G5 and G6, the output of these two, they both have to be zeros. And why is that not possible in return?
Because your input is the output of the other one. It's already negated, so it's going to be the opposite every time.
That is correct, because if Q is 1, then if you follow this one, it goes back into here. And what would that do? It will make the output 1.
Didn't theoretically we said if they both went off at the same time that they would have the same state? Because then it would just be, it would just keep calculating, it would never finish it would just keep looping?
Well, with a D flip-flop, they can both be 1s. I think if all the inputs are zeros, they can both be 1s. Both being 1s is possible if you only look at the D flip-flop. Okay, in other words, I make this one a 0. I make this one also a 0. That would make both of the outputs a 1, output 1s, right? Because these are NAND gates. Remember, it's a NAND gate, which means if at least one input is a 0, the output is going to be a 1. So now the real question is asking, why is it not possible to have this one being a 0 and this one also being a 0? Why is that not possible? Where are they coming from? That's the question. Okay, so let's trace these wires, right? So when you trace this wire, you can see that it is the output of G2. When you trace this wire, it is the output of G3. So can the output of G2 and G3 both be zeros? That becomes the real question. And if it is not possible, why is it not possible? If G2's output is a 0, where is it going? Okay, it's going to G5 as an input, cool. But it's also going to G3 as an input. If G3 has an input, at least one input being a 0, what is going to be its output?
1.
It's going to be a 1. And vice versa is true. Well, vice versa is not true, but it is not possible. They cannot both be zeros. Because as soon as G2's output is a 0, G3's output is guaranteed to be a 1. Yep.
On the test, will we have to explain that? Or?
Yep. That is what you have to explain is if this is the case, that's going to happen, but then it is not possible to have both outputs being a 1. Okay. Very good. See, you don't need Logicsim to do it. Okay, question number 2. Again, observe the design of the edge-sensitive D flip-flop in question number 1. When clock is 0, even with D changing, Q and /Q do not change, which is the whole point of having an edge-sensitive D flip-flop. However, the state of at least one NAND gate does change when you have D itself changing when CLK, the clock, is a 0. State which NAND gate or gates would change their state or the output state when input D changes while CLK remains 0. Okay, so we go back to the diagram, and then we ask the question, we are holding clock to be 0, so that's not changing, but we are changing D itself. So which two gates or which gate or gates can be changed as a result of that? So the first thing you need to do is to look at where clock is going. So clock is a 0, it's going into G2, it's going into G3. So that tells you that G2 and G3 should not be a part of the answer. Because when clock is a 0, it guarantees that G2 and G3 will both be outputting 1s, regardless of the rest of the system. Does that make sense? So the answer has to be either a G1 or G4 or both of those. Is that making any sense? So I'm just applying logic to rule out the ones that I don't even have to look at, just by knowing that clock is being held to 0. Okay, so now I look at G4, and then the first thing I want to know is how does it depend on the clock? It does not depend on the clock directly, which is good news, because one input of G4 is the output of G3. We know that G3 is guaranteed to have an output of 1 already, right? So that means the only other input is from D, so D can directly change G4, the output of G4. Is that okay? So G4 is a part of the answer. The next question is, what about G1? Now G1 is not a part of the answer. Well, let me see, let me double check. Because one input of G1 is coming from G2, which is guaranteed to be a 1. The output of G2 is guaranteed to be a 1. So the only other remaining input of G1 is going to be the determining factor. And that one is the output of G4. So G1 and G4 are both going to be affected by D when clock is held 0. So that would be the answer. Is that okay? So once again, we figure out the answer without logic-sim. Well, because you have the best emulator here. You know, it's just kind of organic and doesn't look the same as a computer.
Doesn't always work right either. I can't do both.
Well, it can do things that computers cannot yet do.
This is true.
But those things are getting fewer and fewer. I think by the time in 20 years, okay, I think in 20 years you look back in time, okay, for in case any one of you are still watching my YouTube, 20 years from now, you would realize, how much progress is going to happen in those 20 years. You look back at those 20 years and you go like, wow. Computers were not able to do X, Y, and Z, at that time, and computers will be able to do those things in 20 years. I think you will find yourself you will find it really rare for someone to have an actual car where you get to steer and control the car in 20 years, because it's just not cost effective to even own your car anymore. Unless you live in the Midwest or some states where it's like 300 miles between any civilization, then you might actually need to have your own car. But if you live around in Sacramento, in the Bay Area, especially in San Francisco, it doesn't make any sense whatsoever in 20 years to actually own your own car. Maybe a Segway, but not a car. Okay, so that's question number 2. This is question number 3. Question number 3, I have to adjust from fall 16, because fall 16 we talk about a different mechanism. So in this case, in binary addition, I give you the actual equation. The result is x naught y plus naught xy, and the carry is just xy, conjunction. Show the derivation of C2 in terms of xi, yi, and C0, where xi denotes the bit I of x, and then yi denotes bit I of y. That's your homework assignment. And yes, you can have a printout of your own homework assignment or my solution to the homework assignment and bring it with you. Is that okay? So one problem of open book and open notes is you have all the material. Can you find the right page quickly enough in the exam? So it becomes a problem of indexing. How do you solve that problem with indexing? So this is the question of, are you going to study the material that you're bringing in? If you bring in like 20 textbooks that you have not read before, but you know the information is in there somewhere, it is not going to be helpful. If you bring in a single sheet of paper that you prepare yourself by going over all the material, you watch the videos again, not every single minute, okay? There's no way you can watch every single minute of all the recording again, but you watch the important part again. And you come up with your own one single page, cheat sheet. Guess how much time it will take you to locate the one part that you need in that case? Small amount of time, okay? So when you go over the material and you make your own condensed version of the notes for this class, for the exam, you're one, studying for the exam because you're going over the material, and two, you're also preparing that printed or handwritten material that you can bring with you to help you in the exam. Okay, so That's how I would study. That's how I studied when in my college days. Okay, so do you still want me to go over this question, or do you want to just kind of leave it? Go over? Okay, so we'll go ahead and do it. Okay, so we basically want to express C2 as something. So immediately, what do you know about C2 or C subscript 2? I'm not going to use the subscript here. It takes too long to answer that. Okay, so we know it is C, the carry of something, or the carry of something, because there are two ways to contribute to this particular carry bit. Which two ways are we talking about?
C0 plus C1.
No. It's coming from the previous digit, right? It's coming from the previous column. So when you add x1 to y1, that's one chance to have a carry to C2. And what about the other chance? Okay, you can still use the notation of W. How many of you still remember W in your homework assignment? In the notations? No? Not really? Okay, fine. Wi is the result of adding xi and yi. I think that's how I define Wi. Okay, so assuming Wi is defined that way, what is the other way to generate another carry?
W1 C naught.
Sorry?
W1 C naught.
W1 is one of those, but not C naught. C1, exactly. Okay, very good. And this is good, almost good enough, except for this R. The W is easy. The W is really just x1, y1 as the result. So we are almost there, except for this annoying C1 here, because we have to express everything in terms of x, y, and C0. Okay, this is a C1. So we have to figure out what is C1. Okay, what is C1?
X naught, Y naught.
Yep, you just do it like that, and plus, well,
X naught plus Y naught times C naught.
okay. There we go. So we are pretty close. And then what do we do? Sorry? You can distribute it. You can put everything in. Okay, but this is going to be the painful way. Okay, let me show you why I mean when I say the painful way. Because now you can say, oh, okay, now we can express C2 in terms of C1, but since we already know what C1 is, we'll just put it here. Okay, but what about using just AND gates and OR gates? I guess I have to change the question a little bit so that I have to ask, express the final answer, but only in using AND, OR, and NOT. Because this is not using those, okay? What is the easier way to do this? There's a generator that we have talked about in class. You guys don't remember? There's a recursive thing too. So that is a better way to do it, okay? This one is by definition, but when you use the other method, it gives you a easier equation. Because this one, if you think about it, it's actually quite involved. Well, maybe not this one. This one is not too bad.
You're talking about the G and the P?
Yeah. But I'm looking at this one and see if it is really difficult. It doesn't seem to be very difficult. So this one you can probably just resolve it too. Okay, so we have x1, y1 plus, and then the carry of this is x1 not y1 plus not x1 y1, and then x0 y0 close paren, and then we have x0 not y0 x not x0 y0 cover z0, and then we just have x1 y1 plus x1 not y1 plus not x1 y1, then the whole thing times x0 y0 plus x0 not y1 not y0 plus not x0, y0, and then the entire thing times c0. I guess it's not too bad. That would still be a correct answer, because we are now only expressing the answer using conjunctions, which is quote unquote a multiplication, and disjunction, which is represented as a plus, and negation, which is an exclamation point. So that's not too bad. But you can always use the generator function that we talked about in class. Okay, do you guys still remember which generation function we are talking about? The ripple carry term? No? Nobody remember anything about that? Even after that homework assignment? Okay, so let's go ahead. Let me point back to where we are talking, what I'm talking about, because when you're studying, you got to study that too. So that will be in data and number representation, and it's going to be in the ripple, not the ripple, but the carry look ahead. So you have to go to adding and subtracting using logic gates, and then go to the look ahead portion. We are there already. And then there's a generator. Okay, I guess somebody can say that the generator is harder to understand than the other way. But this is a generator. It will give you a C whatever, out of the other terms, as long as you define what your G's and your P's and so on.
Can't you use the CN plus 1?
Hmm?
The one below it?
The one below that?
Simplified. Yeah. Whereas
Or you can just use this one. For this particular question, it's already spelled out. But then somebody is going to look at this and go like, hey, this doesn't look the same as the other answer, right? Because this looks so much easier, so much cleaner. But because we only got like x1 plus y1 here, we only got x1, y1, and x0 plus y0. But in the other one, which is this one here, it looks so much uglier. Why do you think this one looks so much uglier compared to the other one when they're supposed to be the same? Because of the simplification. Because we did the simplification part up here. Because of this particular simplification, the factoring, by introducing additional, more specific terms, we were able to do the simplification. That's why this one looks a lot cleaner than the other one. Good job. If you remember, just remember that, oh yeah, we did some simplification and that's why it looks cleaner. That means you still have some recollection when we talk about carry look ahead, which is good. Okay, so are there any other concerns about question number 3? This is okay. It just looks uglier, but it's the same thing. Yep.
You said you were going to write this question differently. Can you explain again how you were going to write this question differently?
Oh, I'm just going to add the part where, so show the derivation of C2 in terms of blah, 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 but only using conjunction, disjunction, and negation in the expression. In other words, I don't want people to stop here. That's the only thing.
And then I imagine you probably wouldn't use the exact same thing. Like it wouldn't be C2.
Unless I forget to change the practice exam.
Maybe it won't be addition, it'll be subtraction.
Can be addition, can be subtraction, can be comparison. Okay, so if you look at C3 and C2, how do they compare? How many more gates do you have to use? That sort of thing. But it will still test your understanding of the mechanism itself. Okay. So moving on to the last question in this particular version. So this is the last question, which is also something that we talked about already at this time. So this one is giving you a sequence of operations, and then it's asking you what does it end up doing? Okay. All right. So I'll just read the question itself. Observe the following memory bus state changes. If nothing is mentioned, the state of that port is unchanged. Okay, so if I don't mention anything on a particular row, it means everything else remains exactly the same as before. based on this sequence of port operations, indicate the actual operation of memory, such as location 72 in hexadecimal is updated to DE, or the content of location 65 is on the D port. In other words, you have to tell me if it is a read operation, what is at the D port as a read operation. If it's a write operation, you have to tell me which location of this RAM is updated to what value. Is that okay? Do you guys understand what I'm asking for? Okay, so let's go ahead and do this as an exercise. Okay, so the first line is basically saying LD load is a 0, clear is a 0, clock is a 0. Now this one remains 0 the entire time because if I set a CLR or clear to be 1, all location will turn back into 1. Okay. LD is a 0 means it is not a load operation. If it's not a load operation, it's a store operation. What is a load operation as opposed to a not load operation?
One is reading, one is writing.
Which one is read and which one is write?
Not really. One is read, 0 is write.
I think it's
0 is a write operation that changes the content of the RAM, and then having a 1 in LD is a read operation where you just get the content of a location and make it the output of the RAM. Okay, so in this case, it is a write operation. I'm about to change something possibly in the RAM. Okay, so the other thing, on top of this, I'm now making the select pin being a 1, which means this chip is now selected. The A port is a 2D, which means I am addressing 2D as the location, and then D is 50, which means I am now trying to specify a content of 50 in location 2D. Do you indicate that this is where a write operation happens? It's not happening just yet because why? Because the clock is not transitioning. Okay. So that means nothing is written. So when I change D to 6E, the 50 was never stored. Okay, I changed the data port to 6E, and then I have a clock transition. So by the time I get to step number 4, then we actually ended up with something being stored at location 2D, but it's not 50. 50 was never stored. It remained on the port, but never stored in that location. It's only 6E that is stored. Are there any questions about this part? Because this is the important part. If somebody gives me the answer of we first store 50 and then we store 6E into that location, I would take points off. It's not entirely wrong, but it is not entirely correct either.
So
Yep.
for each number, say 1, you indicate what's happening in that one. Say 1.
That would be one way to do it. If nothing happens, you can just not write anything.
Oh.
Mm-hmm. Okay, so then we change the clock back to 0, and then we change the address to 50. Whoops. We change the address to 50 and then D to 2D, and then we have another clock. What's going to happen when we have this clock here? Did we change LD from step 4? No, so we are still dealing with a write operation. So this is another write operation. We are writing 2D as the content to location 50 in step 7. This is our second write operation to this RAM. And then we make clock back to 0. D is not driven by the processor. In other words, I'm informing you that the D port is no longer driven by the processor. Okay, which is important because somebody can say, because the moment I change LD to a 1, somebody can complain and say, well, there can potentially be a bus fight. Because if the processor does not stop driving D port, the moment I change LD to a 1 and SEL, the select pin is a 1, both the RAM and the processor will be driving the same lines. Unless they're driving each line, every line set the same way, we can end up with a bus fight. Yep?
In that instance, wouldn't they be doing just that of driving everyone in the same way since you haven't changed D yet? Potentially?
Say that, oh, because they are driving exactly the same way?
Yeah, so far.
So far, yes. Because then the next instruction is going to change because I'm changing the address to a 2D. So if If I didn't specify this, then by the time we get to step 10, we definitely have a bus fight. Because the content from the processor will no longer be the same. The processor can still be driving the D port in a certain way, but then the RAM will also be driving D port, because at this point it is going to be reading the location. Now, when you are writing your answer, this is the tricky part. The tricky part is by step 9, you have to indicate that the D port is now is being driven using the content of location 50, which is having a value of 2D. So step 9, you have to indicate this is reading location 50, which ends up driving the D port with 2D. Is that okay? Okay, so at step 9, you have to indicate that this is the first read operation, and what it is reading is location 50 in RAM, and the content of that location is 2D. So the D port is now outputting 2D, or the bit pattern corresponding to 2D. Is that okay?
Yeah.
Because a lot of people missed this one last year. And then when I change it to, when I change the address port to 2D, then it's going to output whatever location 2D has. And what do you think location 2D has at this point? It's a 6E. Because we wrote a 6E into that location earlier. Yep.
If load is a 1, it'll still read that even without the clock going from 0 to 1, right?
That is correct, because read operations do not rely on clocks.
Sorry about that.
Yep.
So,
Mm-hmm.
so actual writing happens when clock turns 1,
From a 0 to a 1.
or when it changes from 0 to 1?
Only when it changes from a 0 to a 1. So if I write consecutive rows here from the description and say CLK equals 1, and then the next row says exactly the same thing, CLK equals 1, CLK has no transition, so there are no additional write operations.
It was like that element in logicine that was twist turning the clock.
It's the same mechanism as a clocked D flip-flop. So when the clock line is stable with a 1 or 0, there's no change of states. It's only when the clock changes from 0 to 1, then you actually have a store operation.
What about 1 to 0?
1 to 0 does not matter, it's only the rising edge. Yep.
So what happens if, what happens if the processor stops driving D, but you then have a clock change of going from 0 to 1? Like, what would happen in memory?
If the processor is still driving the D port.
No longer driving. So instead
No
of 9
longer driving the D port.
Yeah.
Well, that's a very good question, and I can actually answer that question too. It depends on how much time is between the last write operation and what you just described, which is the data port not driven by anyone, and you are writing to RAM. Is that what you're asking?
Yeah.
If the time in between is relatively short, then there's a pretty good chance that it will just write whatever is left over, quote unquote, on the data bus. Because the traces are basically a capacitor of sorts, okay? So the voltage presented on a particular pin will remain there for a short amount of time. And there's a chance that you might actually end up writing the same content to the next location if the data port is not driven.
Okay.
So you're basically seeing a ghost image, but that depends on how much time is between those two operations. It also depends on how the circuit board is designed. Because if your data lines are next to some other lines that are flipping and flopping at the same time, the inductance of the other wires or traces can induce a different residual signal on the data lines, and then you might be reading something else. So there's no guarantee of what you will be reading, but unless you have interference of some kind and the amount of time is really short, then you can be writing the same content. Yep.
So just curious, like it's a little outside the scope of the class, but now I'm really wondering. So if you could you exploit that to read areas of RAM that you don't have access to if you understand the way that instructions are being executed?
No, because the processor itself is going to stop you from changing the address ports in the first place. So you don't even get a chance to change the address port because you cannot even execute that instruction. But good try. Yep. Oh, there are more questions. I said there were only 4 questions. There are 5 and 6. Okay, question number 5 is complete the following long binary addition. Specify all the borrow bits as well as result bits. Okay, I know why there's an inconsistency because somebody was taking this exam like a week after the actual exam, so I had to make some changes, and I forgot to make some of the minor changes here. So let's make that a subtraction here. Okay. So this is a long binary subtraction, specify all the borrow bits as well as the result bits. So you have to give me a column, like a table kind of thing. Okay, I'll just kind of emulate that here. So let's change the font to something that has a fixed width. That should do it. Okay, so we have, oh, that's not fixed width at all. 0, 0, 0, 1, 1, 0 minus. It's looking at it as a bullet.
Why don't you insert a table?
Thinking how many entries I would need.
Just do some
You can always
extra.
add more.
Okay, 1, 2. Well, we'll need 5, but we also need the lines in between. You know, well, I guess we'll start with this. Okay, so we have 0, 0, 1, 0, 1, 1, 0 minus 1, 1, 0, 1. Okay, so we need to know. We definitely need one more. Oh, okay, there we go. It's on the next page. Let's change this to not to use page layout, because otherwise it breaks it right when we want to get to the result. Okay, so this is going to be by default a 0. Not this one, this one. This is a borrow. This is B0. 0 minus 1, it has a borrow, so we have to set this borrow to 1. But the result of 0 minus 1 is a 1. 1 minus 0 is a 1. 1 minus 0 is a 1. And then 1 minus 1 is a 0. 1 minus 1 is a 0. There's no borrow from the previous column. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. And then there were no borrows from the previous column, so it's a borrow of 0. 1 minus 0 is a 1. So that's what I'm expecting. Okay. Question number 6. Observe. Oops, sorry. Oh, I thought somebody said something. Okay. So in question number 6, we have a register bank, kind of, because even though it looks like a register bank, it also has the multiplier here, a multiplexer, an adder, and another multiplexer. So the question is asking, assume the music box register starts with a value of 0. This is your music box register. Specify the content in ROM. Use as many locations as needed. Assume the width of D is 9 bits. To accomplish the following, I want to multiply A and B and then add the product to C, and then I want to multiply A and C and then add the product to D. So how would you do that? Okay, but how do you get started with this one? Okay, first of all, we need a multiplication, because the order of operation means we have to multiply first and then we do the add. So you have to look at the multiplication. Fortunately, we only have one multiplication operation here, so we can focus on that one thing. So we focus on the multiplier, like this one here, and then you say, okay, we need one side of the multiplication to come from register A, we need the other one to come from register B. So we need mux, this mux to connect to register A, which is this one, and then we need the second mux to connect to register B. Is that okay? So you always start with the intent, okay, what you need to do. And then you ask the question of how do I make that happen? Is that okay? So what do you have to do to make that happen? You look at the mux. How do you control a mux? I took out all the other bits, going into a mux to make it kind of relatively easy. So the only one left would be these lines, right? This is the line to select which input becomes the output. This line becomes, the specification of which input becomes the output. Is that okay? All right. I need input 0 to be the output for the top mux. So when you look at this line here, okay, you track it down, and you may not be able to see it in the class because it's kind of small, but it says 2 to 3. Bit 2 to bit 3 they need to be 0, 1, or 0, 1. What would be the bit pattern for those two particular bits? Okay, so this is a good time to kind of write it down. You can write it down on a piece of paper, but I'm just going to write it down on a whiteboard. The ROM has 9 bits. Okay, so we got bit 0, 1, 2, 3, 4, 5, 6, 7, 8. That will give us 9 bits. We know that bit 2 to 3 is responsible to control the top mux feeding into the multiplier. And we also want that needs to be connecting to register A, which is input 0. So that means bit 2 and bit 3, they need to be zeros. We also know for the bottom mux, we want to connect it to the first register one, which is register B. So the control line to the bottom mux is going to bits 4 to 5. So we know these two need to be a 0, 1. Is that okay? What else do we have to specify? Well, we want to add to register C and then store the result back to register C. There's only one adder here, but the input of this adder, one of the input comes from the multiplier, which is good because that's what we want. But the other input of this adder is coming from this other mux here. This mux connects to exactly the same 4 registers, and in this case, we want to add C to the product. So register C is basically the third one, but because we count from 0, it is input 2 to this particular mux. The control line of this mux are bit 0 to 1. So what do we need to specify as bit 1 and bit 0?
1, 0.
Just 1, 0, okay? Because that's how we specify register C. So this is specifying register C, this is specifying register A, this is specifying register B. Okay, but which one is going to store the result? According to the C expression here, we want register C both to supply the number to be added, but also to store the result. So that means the output of the adder, it needs to go back into and change one of the registers. It's going to be the same register here. But how do you specify which register is going to be changed in this particular picture? If you look at the registers, which line or which port of a register controls whether it is enabled or not? The EN, okay, very good. And in this particular picture, how do we control the EN of a particular register? The decoder, okay, which is kind of like a demux, but it's kind of specialized. So it is the decoder, very good. So of the decoder, the one with a dot, okay, let me see if I can point out which one. So the one with a dot, which is this one here, that is how you select. And that one, if you trace the wire, it goes to bits 6 to 7. So what do I need to put in bit 6, 7? I need to update register C, so register C is the only one that needs to be enabled. It will be the same as this one, which is 1, 0. Very good. Okay. And what about bit 8? Bit 8 is connecting to the other port. And what do you think that one is going to do? Enable, okay? So that means, it has to be 1 to actually do something. So this becomes the bit pattern, the first bit pattern that you need to accomplish B plus equal to A times B. Once you figure out the first one, the second one is easy because you're only changing a few of those bits. Is that okay? Oh, there's one more thing. We have to kind of remember that too. The clock, you have to wait for the clock to transition to. Because the register won't do a single thing even if it is enabled because it's still waiting for the clock line to clock. So the clock line has to clock, you have to see a rising edge of the clock and then you move on to the next instruction. Note how the clock is connected to all the registers. You may also assume the clock line starts with a low state. The decoder has an enable pin. If the enable pin, okay, I just explained how to use the decoder. If the enable pin is a 0, then all outputs are 0. If the enable pin is 1, then the output pin that is selected is a 1 where all other pins are 0s. So it's just a short explanation of what the decoder does. All registers are aided by the ROM has an 8-bit A port or address port, and it's a 9-bit D port. Okay, so this part is incorrect, it should be a 9-bit D port. To avoid race condition, the music box register updates on falling edges and so on. So this space is reserved for the answer of question number 6. So you may specify content in ROM in binary or in hexadecimal. So it's up to you to decide how you want to represent it. I personally would just use binary, just do a 0B, so I know it is a binary number. Is that okay? So you only have to specify 2 locations. So this is the first location, and then the second location is going to reflect the next one. So once you identify which ones are the C's and which ones are the A's and which ones are the B's, you know which one you have to tweak for the next instruction.
Okay, so that's it.
This is the first location. So to do the second location, you keep the A's the same, right? So this one remains exactly the same, and then the B becomes a C. So this one needs to become a 1, 0. This one remains as a 0, 0. And then the C's becomes D's, right? So this one becomes a 1, 1. This one becomes a 1, 1. And bit 8 still has to remain as a 1. So this is your second location. Yep.
So all the explanation of the actual diagram, all we're giving you as the answer is just those 2 values.
Yes.
Okay. Cool.
Yep. So the answer that you have to give me is just these 2 lines.
Okay.
And it's safe to assume that's like ROM address 1, ROM address 2.
Correct.
Yeah,
You have to specify location, which one is location 0 and location 1, because the music box register starts with a value of 0. So you have to say that this is location 0, this is location 1. Good point. Yep.
Do we need to specify, like, wait for a clock?
You don't have to specify that because the music box mechanism is the same one that you have seen. So the music box register has its own clock, which is this one, hooked up to the clock signal as well. So you don't have to specify, oh, we have to wait for clock low, clock high, because the music box mechanism takes care of that already. And there were a few, yep, go ahead.
So for the second one, the C becomes
The C becomes a D because the C are these 2 bits.
okay.
This is a leftover one for controlling whether the decoder itself is enabled or not. Okay. So obviously I'm not going to ask this question again. So I can ask this kind of question in a reverse way. I give you the bits, and then you tell me what's going to happen. But the idea is you still have to be able to understand all of the components of the processor that we have talked about. And I'm going to give you, something that you may not have seen before, but it will still be using the same components. Yep, I just put all the parts into a box, shake it a little bit, and it becomes a new question. Alrighty, so I'm not sure what to give you as a new homework assignment. How many people successfully did the previous homework assignment? Okay.
Believe me, successfully did.
Okay, because if there's a really low number of people who got it right, what I wanted to do was have you guys to do a reflection on your own program and explain why it is not working. I guess we don't have to do that. Unless you guys really want to do it. No, okay. I can see people shaking their heads. Okay, so it's a good time to start studying because on next Tuesday we still have one more meeting. So after you study and you have some questions about certain parts of what we talked about, Tuesday would be a good day to ask those questions.
I'm one of the people who didn't turn it in.
Okay.
But I had